This video we will talking about the potential energy method to derive the element stiffness, and we will starting with the simple one, that is a spring element. Before we talking about the potential energy method, we have to just talk a little bit with the principle of virtual work first. That actually we have studied this principle uh, in engineering mechanics and also in mechanics of material. And we know that if a deformable body in equilibrium is subject to arbitrary, virtual, or imaginary displacement associated with a compatible deformation of the body, the virtual work of external force on the body is equal to the virtual strain energy of the internal stress. Okay, this is the principle of virtual work. That is maybe write in the equation form like this, and delta U represents the virtual strain energy. The virtual strain energy that is due to the internal force or due to the internal stress, and delta W is the virtual work of the external force on the elements. Okay. If you just come back to review in engineering mechanics one, we will talking about just only rigid body. The rigid body is state for the rigid body principle virtual work is state that the system is in equilibrium. It's just for the virtual work done is equal to zero for that. Okay, but if the for the system that is the deformed body is not the rigid body anymore, the structure can deform. Okay, so we apply the principle virtual work, and it state that we for the deformation body we have the strain energy also. So the principle of virtual work is maybe half the, it has this term also, that is the term of strain energy, and it state that virtual strain energy due to internal stress equal to the virtual work done by the external force. And this is the equation for principle of virtual work. And we will have to note that the principle of virtual works can use in many types of problem, in a lot of problem, also includes of linear and nonlinear. It can use for nonlinear problem, also nonlinear problem, and especially it can use for the conservative system and non-conservative system. Okay, it can apply to solve every type of problem, both for conservation problem or non-conservation problem. For the conservative system, that is about the problem that we talking about just only the conservative force. But for non-conservative system, it's just we the system maybe have a non-conservative force also. The example of non-conservative force is just the friction force is one type of non-conservative force. Okay, and uh, according to this, we will scope uh, to the principle that we will apply for the case of finite element that we scope to, that is scope to this study. For our course, we scope the problem just only for the linear problem, elastic, and conservative. Okay, so according to that, the principle of minimum potential energy can be applied. Okay, so for this case, okay, we will right now, after this, we will apply this principle. That is state that is the principle of minimum potential energy. That is principle of minimum potential energy. And actually it's this principle is actually, it is the limit to conservative system. Okay, it's limit to conservative system only. Okay, but it can apply for both linear and non-linear also. Linear problem or non-linear problem can be applied. Okay, we can apply this principle to both linear or non-linear. But this course, we will scope just only the linear. Just for this course, we scope just only linear problem. Linear. That is, we talking about small displacement. Linear problem, that is maybe something like the small displacement. And we're talking about the linear material. Okay, linear material. Okay, according to the principle of virtual work, okay, if we apply the principle of virtual work first and then we use the calculus of variation, that we will not talking in depth about this method. Okay, we will obtain the principle of minimum potential energy also. Okay, this is let's be talking about the potential energy of the structure first. Okay, right now the potential energy, we may write it in the note. We use the pi notation. Pi notation represent the total potential energy, represent total potential energy, that is equal to U plus omega. Okay, equal to U plus omega. U represent strain energy and omega represent the work done. The work done due to the external force, the potential energy due to the external force. Okay, so according to this, if we talking about the total potential energy, that is represent pi term. Okay, it is the sum of internal strain energy, that is represented by U. Okay, and the potential energy of the external force represented by omega. Okay, represented by omega. So right now we know that the potential energy is equal to strain energy plus the potential energy due to external force. Okay, and the strain energy is derived from the internal force, that is come from the axial force, shear force, and also bending moment. Okay, but the omega is from the external force, that is composed of the body force, the surface traction force. Okay, body force, that is maybe included itself weight also, and the applied nodal force, that is work to that's to do work through the deformation of the structure. Okay, so let me starting with the simple one, the simple structure, that is the spring. That is spring. We know that the spring with the spring constant K has the relationship between the applied force to the internal force, that is Kx. Okay, so we have the force of the spring. the force related to the deformation of spring by this equation F equal to kx. Okay, so from this, if we plotting the graph, we have the relationship like this picture. F equal to kx is a linear spring for the case of linear spring. And if we consider the differential internal work or differential strain energy that's represented by du, okay, and F represent the internal force, internal spring force, okay. So the strain energy or the work done due to the internal force can be represented by this equation, okay. Du is equal to F dx, okay. If we substitute the force F that is equal to kx into this equation, we obtain du equal to kx dx, okay. So according to this, if we integrate both sides, we obtain u equal to integrate kx dx. And then if we substitute the limit of integration from 0 to x, we obtain that the strain energy due to spring is equal to a half kx squared. Actually, we already know this term from physics, from fundamental physics, that is derived from the strain energy that we already done, right? Okay, according to this, we know that the strain energy of the spring equal to a half kx squared. Or we may write it in terms of force by this. It is equal to a half kx is the force inside of spring, so it is equal to F and also x. So the strain energy of the spring is equal to a half kx squared or a half fx. Then if we talking about the potential energy of the external force, omega, okay, actually the potential energy of the external force is equal to the opposite inside, okay, opposite inside from the external work done expressed, because the potential energy of the external force is lost when the work is done by the external force, okay. So this means that omega is the potential energy of the external force, and it is equal to minus work done by external force. So if we consider the spring, and the spring has the work done F, have the force F applied to the spring, okay, and the deformation is in the same direction of the applied force. So the work done due to the force F is the positive Fx, okay. If the spring has deformed with the x, okay, so the potential energy due to the applied force is the negative inside, okay. So we found that omega equal to minus fx. And it has to note that if you come back and review a little bit in mechanics of material or in fundamental physics, you will see that why the potential energy due to the external force is opposite inside, because the negative sign provide what? Provide the convention that work done against the force field increase potential energy. But if for this case that we're talking about, it is the case of the work done by the force field, it's decreased potential energy, okay. So according to this, if we come back to form the potential energy for the spring element, we found that the total potential energy of the spring is equal to a half kx squared plus omega, that is omega is equal to minus fx. So the potential energy is become pi equal to a half kx squared minus fx, like this. Okay, so right now we already have the potential energy of the spring. Before we go further, we have to consider the concept of stationary value of the function that we have learned it from calculus. If we imagine that we have the general function g, that is maybe the curve like this picture, okay, and we can see that is maybe the minimum value and maximum value as shown in this picture. If the curve is concave like this is a concave upward, okay, if we consider the point that the slope is equal to 0, for that case it means that dg by dx equal to 0. That is mean that the slope of this function is 0. It may be happen into three cases, at least three cases. That is, it may be the minimum value like this, or it may be the neutral, that is maybe at the point of the chain in curvature, the point of in chain of curvature, it's maybe the critical point or something. And another case that is maybe at the maximum point, that is the concave downward or the convex curve, okay. So according to this, that is the based on the calculus, we found that if we take the first derivative to the function and set it equal to 0, we can find the critical point, that is the slope equal to 0. It may be happen into three cases. This minimum value is neutral or it is the maximum, okay. So according to this, if we come back to the principle of virtual works that is written in the form of calculus of variation, we will find that if we have pi is a functional, that is a function of the function in terms of the degree of freedom d1, d2, d3 and so on until dn, okay. So based on calculus of variation, okay, we can write the variation of pi, okay, by this equation, that is maybe represent to, if we would like to minimize the function pi, okay. So but as we know that the variation of d1, variation of d2 and variation of d3 and so on, variations of dn, they are not equal to 0. They are not equal to 0. If they are 0, we will obtain the trivial solution, that is the no meaning for that. So if we imagine that if delta d1, delta d2 and so on, delta dn is not equal to 0, according to this equation, when we take the variation to pi and set up it equal to 0 based on the principle of virtual work, okay, and we will find that the term, this equation, we for the case of variation of d1, d2 and d3 and also dn is not equal to 0. So from this equation we will obtain n equation that is represent variation pi partial derivative the function pi with respect to the nodal displacement di, or we may write partial pi by d1 equal to 0. This is the first equation, right? And then partial pi with respect to d2 is equal to 0. That is the second equation, and so on. Okay, So we get an equation. We get an equation for this case. Okay. So in order to according to this equation, we found that, okay, because we set up partial pi by partial di equal to 0, so it's become to the principle of minimum potential energy. Okay, it will become extend to the principle of minimum potential energy. Okay, and then before we go that, we may consider the simple example like this. Okay, in order to illustrate the potential energy of the spring system. Okay, if we consider the spring element, that is just only one spring, and the spring has a stiffness K equal to 500 pounds per inch. Okay, and the applied force is 1,000 pounds. Okay, and spring is the linear spring. So when we form the potential energy equation, if we form the potential energy equation, we found that pi equal to u plus omega, right? And after we apply pi equal to u plus omega and u equal to a half kx squared, and then omega equal to minus fx, so this is a half kx squared minus fx. Okay, according to the principle of virtual works, okay, from this system we have just only one degree of freedom, that is x. So when we take the relation, we have this term relation pi equal to partial pi by partial x, relation x, and we know that relation x is not equal to 0. So we obtain partial pi by partial x equal to 0, right? That is, from this equation, what does it mean? It means that the partial pi, the function pi is constant, right? Or it is the stationary. Okay, so from this equation we may state that this equation is maybe state for the stationary potential energy principle. Stationary potential energy principle. Okay, according to this, you see that it is come from the principle of virtual work, and then after we apply to that, it can minimize to the term of stationary potential energy. Okay, and according to this, if we take the first derivative to this equation, minimize the term of potential energy is a half kx squared minus fx. So the first derivative of pi with respect to x, we obtain this equation. Actually, if you see, okay, so partial pi by partial x is equal to kx minus f. Okay, if we set up it equal to 0, so we found that it's equal to kx equal to f. That is, come back to the term of the force of spring, right? Okay, so according to this, if we consider for the case of the first derivative of pi equal to x equal to 0, So we obtain x equal to 2. And if we substitute back x equal to 2 into the potential energy, okay, we obtain the potential energy equal to minus 1000 pounds in. That is, we will show next that this value is the minimum value of the potential energy. Okay, so if we consider the potential energy in terms of x like this, and we derive it, and also we plot it with a graph, okay, you see that at x equal to 2, at x equal to 2, we obtain the potential energy equal to minus 1000. That is the minimum value of the potential energy. Okay, that is the minimum value of the function. Okay, so according to this, if we would like to derive the spring element equation by using the principle of minimum potential energy, or actually it is just only the stationary potential energy principle. Okay, we may starting with write the potential energy equation first based on the spring element that we already define like this. Okay, the spring has two nodes, and node number 1 has the deformation of d1x, node number 2 has the deformation of d2x. Okay, so the deformation of the spring due to the displacement, the nodal displacement d2x and d1x is equal to d2x minus d1x. According to that, when we substitute into the potential energy equation, this is the term of strain energy. This is a term of the work done by nodal force. Okay, the work done by nodal force, that is F1x d1x. But if we write them in the term of potential energy due to the external work, it should be half the negative sign like this. So in the same manner for the nodal force in the node number 2, we obtain this. And then after we expand the term, of the strain energy, we obtain this equation. And then we take the first derivative. To the potential energy equation, that we have to take the derivative with respect to d1 first, and then for d2. Okay, so you see that, and we set up is equal to 0. We see that we obtain two equations, right? First one, we take the first derivative of pi with respect to d1. We obtain this equation. And then we take the first derivative of pi with respect to d2. We obtain this equation. So, and after that, because it is the stationary position, that is the first derivative of pi with respect to the degree of freedom is equal to 0. So for that case, we have two equations, and we can rearrange it into this term, into this equation. Okay, and after that, we write it in the term of matrix, and then we found that we obtain the stiffness metric that same as the direct equilibrium method that we already done before, that we already know it before. Okay, so according to this, you will see that the principle of minimum potential energy, or principle of stationary potential energy, always use the energy method. We obtain the same element stiffness. Okay, but you see that the procedure is straightforward. It is straightforward. The starting with forming the starting with forming the potential energy pi equal to u plus omega. If we know strain energy function u, and if we know the potential energy due to external force omega, okay, we just take the first derivative of pi with respect to degree of freedom, we will obtain the stiffness equation, okay, the element equation. Okay, that is straightforward. It's not necessary to consider the equilibrium of the system, that in some case we don't know the equilibrium position. Okay, so it's maybe not convenient to derive the complicated for the complicated element type. Okay, for complicated element type, normally we apply the energy method like this to derive the element equation. So this is just the overview of the energy method that we will talking about it again and again. Okay, just now, just remember that pi equal to u plus omega, that is the potential energy, and after that we will derive the element stiffness by take the first derivative of pi with respect to di, that is the for each degree of freedom. Then we obtain the n equation with n degree of freedom. Okay, so we will talking about the potential energy method again for the bi-element, but and for now we should end of this clip.